Good, alhamdulillah. رمضان مبارك يا رب. Yes. Mm. I will have a look right now. Because from what remember the last conversation that we had with you, I think the next action items were on you, like you were awaiting some information. But I'll go back, I'll look at the email and I'll reply to you today, inshallah. Okay? Okay. Thank you very much, Khalid. Nice talking to you. Assalamu alaikum. So, who is Muhammad Mugarrid? Nothing, nothing. No, no, no. Just someone mentioned you, and I couldn't connect the name and the face. Wanted to see. Okay, assalamu alaikum everyone. How are you guys? How is it going? Happy that today is the last day of the course. This is the last of the course in Ramadan. I'm happy. I'll be a bit relaxed now. Let's get through the last day, inshallah. So you have a homework assignment for this week. We had originally planned for two exercise sheets, one for reinforcement learning with human feedback and one for Arabic to English translation. I'm going to drop the second one. And I'm going to give you guys one exercise, which is English, Arabic to English translation. Okay. So in the evening session, Ali will walk you guys through all the details of it. We just wanted to give you guys a high level overview of what the homework exercises. So just one exercise for this week. Okay. Let's give one more minute for people to join in, and then walk you guys through the agenda for today. So we'll do a quick review of reinforcement learning with human feedback, proximal policy optimization. I'm not going to walk you through all the details of it, just high level summary of what was the main purpose. And then we would look at through recent incarnation of reinforcement learning with human feedback. One is DPO, direct preference optimization, and the other one is GRPO, group relative policy optimization. Both of these have some smart thinking behind that. So I will develop the setup for it, and then we'll see like how they make our life easy in doing reinforcement learning with human feedback. So, okay, so I think we are good to go. Can someone check that we are okay on the Zoom as well? And screen is there and everything is good. Okay. Okay. So let's start with a quick overview of what we did yesterday. Okay. So typically when we train a large language models, we have three steps of training. Okay. We have, what is the first step? Step one is pre-training. Pre-training is basically just learning to produce tokens in a language. So it's basically just learning the language. Okay. Then we have step two, which is supervised fine-tuning. So this is general data for the internet. This one is high quality task specific data. And then finally we have reinforcement learning with human feedback. Okay, where we have RL setup with reward model, go to okay, that's the setup. Okay, so I have a question for you guys. So what are the advantages of reinforcement learning based setup over supervised fine-tuning? No. In terms of like, because what do we want to do? Eventually, we want to produce language. We want to do a task. We want to have a chatbot or a math tutor or a language translator or so on. What is it that reinforcement learning with human feedback can do that supervised fine-tuning cannot do? Because if supervised fine-tuning can do everything, then we just don't need reinforcement learning with human feedback. Okay, that's one thing. So supervised fine-tuning essentially is max likelihood approach. Okay. It will just tell you which data to make more likely. It could not tell you which data to make less likely. Of course, because you have a distribution, if you make the things which you want more likely, implicitly it would make the things that you don't want less likely, but we don't do it explicitly. Whereas in reinforcement learning, it's some sort of a weighted max likelihood, where the weight is from return. Okay. So it's basically, it tells you how good an answer is, how good an output is. And then if the output is good, you increase its probability. If the output is bad, you decrease its probability. That's one advantage. And another advantage that I did not specifically mention yesterday is that supervised fine tuning is static. Okay. It's some data that you have collected from the internet. Whereas reinforcement learning with human feedback collects dynamic data from your network. So think of it like this. Supervised fine tuning is essentially, if I give you a book which says how to play football. Okay. So it's a general book. It's not relevant to you. Okay. You're reading this book and try to learn football. Reinforcement learning with human feedback asks you to play football and then see which mistakes you are doing and fix those for you. Do you see the difference between the two? Okay. So one is just a manual. Supervised fine tuning is just a manual. Reinforcement learning with human feedback is a tutor. It's sitting with you, it's observing what you are doing and trying to fix it for you. Make sense? Yeah, this is another advantage. It's implied, but I did not explicitly mention it yesterday. So I said, okay, let's mention it today. Okay. So continuing with our review, okay, what is the goal in reinforcement learning? I'm not going to go over a review of what an agent is, what an environment is, what a reward is, and what strat dynamics is. I'm assuming that we are all expert in it now. Okay. But what's the goal? What do we want to do in reinforcement learning? So, no, take a step back. Okay. So what is the goal? The goal is achieved by maximizing the likelihood that you mentioned. But what do you want to do? Okay, I'll make the problem slightly easy. Let's say you have a reinforcement learning algorithm, which is helping you invest in the stock market. What would you want it to do? Exactly, that's exactly what we want reinforcement learning to do. We want it to maximize the expected return. Okay, that's it. The goal is we are doing an operation, we are doing something, at the end of which we are getting some rewards, some returns. I want those returns to be maximized. A very simple objective, as it's very similar to how we do things. Okay, I'm sitting in this class, or you guys are sitting in this class, you're spending 3 hours, 3.5 hours every day. The goal is to maximize the return for you. You should learn something. That should be the goal. Okay, so the objective is to maximize expected return. Remember, I'm putting the word expected in it. I'm not putting in return because these are probabilistic processes. Okay, exactly. So you have policy which is probabilistic, you have dynamics which are probabilistic. Okay, so on average you will win, but it's not necessary that you will always win. This is a very good scene from a movie. It's called 21. So it's a professor, and they ask a class is that if I give you a scenario, if I tell you that there are 3 doors, let's say 1, 2, 3, and I tell you behind one door is a car, and behind other 2 doors it's empty. Okay, and I ask you choose a door. Okay, let's say you say I'm choosing this door. Okay, now what I do is of the 2 other doors, I open one of them and show you that there is nothing behind it. Then I ask you, do you want to change your answer? Okay, what do you guys think? Would you change your answer or not? Again, the scenario is you have 3 doors. Okay, behind one door is a car, other 2 doors is empty. And I ask you to choose one. If you select the door with the car is of course yours. Okay, so let's say you select this door. You said that I would check the center door. Now I don't open the center door. Of the other two doors, I open one door and I show you there is nothing behind. And now I give you an option. Okay, would you change you want to stick with your original answer, or you want to change your selection? What would you guys do? Okay, who wants to change it? Okay, only Muhammad, two guys, three guys. Okay, so the correct answer to this is that you should change it. Okay, the reason for this is that when you made your original choice of the door, you had 1 in 3 chances of success. Okay, now that I have opened a door for you and showed you that there is nothing behind it, you have 50% chances of success if you change the door. If you do the exact situations, all situations, then you can't. You do. Now, of course, it is quite likely that you change and there is nothing behind that door, but in expectation, you will have a greater chance. Okay, so if you do it in a game show and you don't get a car, don't come to fight with me, because it's an expectation that you will win. You will not win every time. So that's the concept of expectation. Okay. Again, another example that I want to quote is that if you tell someone, most of you are still young, if you tell someone not to speed, they will tell you like, oh, I've been speeding for 2 years, nothing has happened. This is true, nothing has happened. But in expectation, speeding is way worse than not speeding. Okay, so just because it so happened that the samples that you have picked are from out of distribution or slightly on the lower probability, it does not mean that the high probability event does not exist. It exists, it's just you haven't sampled it yet. Yeah. What are we expecting? What is the expected return? Okay, so that's a good question. So the question is that, okay, I understand this entire setup of RL, but language model is just next token prediction. Okay, how can next token prediction give me a reward? Okay, and I will walk you through the setup for it. Roughly speaking, the setup for it is this. Most language models, what they do is they will have a question. Let's say, in fact, let me create like a small data set for it. So question, answer 1, answer 2. Okay, so let's say the question is, what is the capital of Saudi Arabia? Okay, the answer is Riyadh or Jeddah. Okay, the second question is, the weather in KSA is hot, mild, okay, and so on. So you have these high quality data where you have a question and you have 2 answers from it. Okay, and what you do is you ask a user, a human, to rank them. Okay, so a human would say that this is the right answer of these 2. This is the right answer of these 2, and so on. You have this for entire data set. Okay, using this data, you train a model, which is called a reward model. So you have a model. Let me write it with P, because theta we write language model. Okay, so this reward model, when you give it a question and a corresponding answer, it will give you a score for it. Okay, the score would be between 0, well, not necessarily, it will be a real number. Okay. And for answers which human give a high number, this real number would be high. And for answer which users don't like, this real number would be low. So this is now your reward model. So whenever you have a question and a corresponding answer to it, you can see how much reward you will get for it, or in this case, how much return you will get. There is a what in the process? Yes, there is some annotation in the process, and you might have noticed that the companies, large language model companies, OpenAI, Google, they actually collect this data at times from you. So sometimes you ask a question, you get 2 options. Have you seen that? They tell you which one is better, which one do you like. This is what they are doing. They are collecting the data from you. Okay. Now, of course, we can have cases where we have just a question, we ask the user to write two answers and then do it, but they're not doing it. Remember, they are getting the answers from the network. Okay, because like I said, reinforcement learning is a tutor. It's getting two answers from the network and then selecting the one which is better. So it's slowly and gradually fixing the mistakes of the policy network. Okay. Okay, so I will elaborate a bit more on it. Okay, but let me just continue with the natural flow. So the expected return, this was the expectation for trajectories which are sampled from my policy network. Okay. GFK. This is the first step. And we built on top of it, we said this would be probability of tau, probability of course induced by my policy network. G of tau. And then essentially the whole set of techniques that we saw, they were looking at the gradient of this. The gradient of expected return with respect to parameters of the policy network. So the idea is directly you change theta such that this expected return increase. Okay, this is a simple optimization problem in principle, of course, in application and implementation, it might be a bit tricky. It's a simple problem. You essentially set your problem up as you have an expected gradient, an expected return. This expected return depends on parameter theta. Take the gradient of expected return with respect to theta and take steps in ascent direction. Okay, so we did this setup and we looked at different algorithms for it. So the first algorithm that we wrote was reinforce. Okay, and reinforce was summation I equal to 1 to n. N is the number of trajectories. Okay, summation j equal to 1 to mi. Okay, and you have log of 5 theta of aij given as ij. Okay, so given a state on a trajectory, what is the probability of taking an action? Multiply it with the expected return of that trajectory. Yeah. This is reinforced. And very quickly, we can observe a few things. We can see that this part is exactly like what? This is exactly like maximization of a log likelihood which you maximize. Okay, so this is the log likelihood of data. But where the difference comes in reinforces that you have the multiplication with this quantity. So now it's in some sense, it's a weighted log likelihood, where the weight is the expected return, or shouldn't call it expected. Let's call it's a return on a trajectory. Return on a trajectory. Okay, that's the main setup. Okay, the next algorithm that we saw, it's a maximization. Yes, this is a maximization problem. I'm sorry. No, this is just the objective that we are trying to minimize. So okay, so this is the reinforce objective. This is the objective that we are trying to do, and of course, we'll take the gradient and take a step in the ascent direction. Okay. So the next is actor critic. Okay. So actor critic, we essentially had some modification of the reinforce algorithm. So this was 1 over n summation I equal to 1 to n, j equal to 1 to mi, log of ij. Okay, but now here we had some sort of advantage function. Okay, this advantage function, actually, let me remove this for now. This advantage function essentially is q of si j ij minus v of si. Can somebody explain to me what this thing is? Okay, so I want an explanation of what this advantage is and then an explanation of each term. Okay, so on the Russian. Yes. So we'll try. Okay. 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 So let me take a step back. So in reinforce, what did we do? We had the weight of full trajectory, right? And we made the trajectories which were good, very likely, and trajectories which were bad, we made them less likely. I would make it clear that we can break the task down into slightly simpler tasks. Okay. What I will do is that I will go to each state and I will see what is the current policy in this state. Okay. Based on this current policy, how much am I getting? So let's take a simple example. Let's say that I have I'm investing in stocks. Okay. And my policy is that at 10 in the morning, okay, when the stock exchange is open, just divide my portfolio equally into the 5 companies which have lost the most value yesterday. Okay, that's a policy. Might be a good policy, it might be a bad policy. Okay. Essentially, let me repeat. By 10 in the morning, I take my money, let's say I have 100 and I divide it into 20, 20, 20, 20. Go look at the yesterday's result and look at the companies which have lost the most value. Buy 20 real stock in my fund. This is the policy. And of course, if I have this policy, I can check how much return I will get from this policy. How will I check it? I will go and look at the record of yesterday, day before yesterday, day before yesterday, and so on, and just see how much money I collected from it. This is the value of my strategy. Okay? This is how much I would earn from my strategy at the current day. Okay? At the state of my day, I have my policy. I can just is that look for the company which has lost the most value over the past 1 year, and it's below the average value. Current value is below the average of the last 5 years. Okay, invest in that. Now I'm giving you in this current state. I'm giving you a new action. You had an action which was $20, 5 companies. I'm telling you use this new policy, invest with that. Of course, you can simulate. You can see how much return you will get. You can wait till the end of the day, and you can see how much money you will get with this new action, this new strategy. So this new strategy is Q as a bet. So I'm giving you a state. I'm giving you an action as well. Okay. So this is the Q function. The assumption is that from tomorrow onward, I will keep everything. It's just for today that I'm doing a different action. Okay. This is Q as a bet. If this thing is positive, then it implies that making this modification to your policy, okay, is better, because this action is better than the value of your policy in this current state. So essentially, I'm making a small tweak to my policy in this current state. In this current state, I'm modifying the strategy such that it puts a little bit more weight on the action, which is better than the average value of the state using the current policy. Does this make sense to everyone? Everyone is clear? This is essentially the advantage. And this setup is called actor critic. So why is it called actor critic? Because it has two components. It has an actor, this policy network. This is an actor. It performs an action. It takes in a state and it gives you an action. But then it has a critic as well. So this thing, this part is the critic. Okay, and more specifically, this is the critic, the value function, which takes in a state and gives you the value of that state. Okay. So essentially, you will do an action, and this part of your code, this would look at your action and it will criticize it. It will say that, hey, this is a good action, do more of it. Or this was a bad action, do less of it. Okay. So the algorithm's PPO is essentially an actor critic. You have an actor and you have a critic. Okay. So the third algorithm that we saw yesterday was PPO. Okay. So Mohammed, if I'm making a mistake, correct. Okay. I'm going to write the expression for PPO, hopefully fine. Okay. So the objective for PPO is summation from t equal to 1 to t. Under the new policy, the probability of an action given a state divided by, under the old policy, probability of an action given a state. Okay. Let me just remove this for now. I'll tell you why I'm doing that. Okay. Then you have the same quantity . See? AP and ST, but this time it's clipped. Okay, it's clipped at 1 minus epsilon and 1 plus epsilon. Okay, I take the minimum of these two and I multiply it with the advantage function and 60 and 80. Okay, essentially what you're doing is you're taking the ratio of the new policy with the old policy, multiplying it with theta. But you don't want this ratio to be more than 1 plus epsilon and to be less than 1 minus epsilon. Yeah. That's the objective. Yeah. I will explain what this does exactly. Okay. Along with that, this is, I will call it J theta. You can also have another J value function where you have value of S is summation from t equal to 1 to infinity, the discounted reward, beta t minus 1, reward at t. This thing. Okay. And finally, you have J of exploration, which is essentially the log of AT given ST summation over all actions. Okay, so entropy is with a negative sign or with a positive sign. It's the negative sign. Okay. So what you want to do is you want to maximize this quantity, you want to minimize this quantity, and you want to maximize this quantity. Let me explain all three of them. Okay, this is the PPO algorithm. Okay. Let's look at the first. Okay. So for the time being, let's ignore this part. Okay. Let's just say that this is our objective. Okay. So our objective is probability of an action from the new policy network divided by probability of an action from the old policy network times the advantage. And you want to maximize this quantity. So my question to you is, if the advantage is positive, let's say that for a particular straight action pair, the advantage is positive. How would you need to change the new policy? How would you need to change the new policy to maximize this quantity? Remember, you are changing the parameter theta mu. Theta is what you are changing. So the question is, advantage is positive. What changes do you make to phi theta mu of AT given ST? You tell me. Okay. So if it's positive, then it means that of course you want to do more of this action. Okay. So what would you do? Yeah, update the policy, but how? And they said, okay, roughly speaking, you are going in the right direction. So if I tell you that advantage function for a straight action pair is positive, then what you should do is make this ratio greater than 1. Okay, which essentially means is that you just put more probability on this action. If I'm telling you, okay, you have a policy at this state and you are getting an average return of 10. I give you a new action. I tell you, if you do this action, you get an average return of 12. Now, how would you change your policy? Of course, you will change your policy to do more of this action because I just gave you a better action than your policy. Okay. So how do you increase the probability of this action? You make this ratio greater than 1, which means that you increase this quantity. Okay. That's basically the full intuition. Okay. So let's look at the other way. If the advantage function is negative. Okay. This is negative. Remember, I'm maximizing this quantity. How would I change phi theta mu of an action? How would I change the probability of that action under the new policy if the advantage function is negative? Okay, you see, you are maximizing the quantity. Okay, maximizing the quantity means if I make it very simple for you. Let's say I tell you this. I tell you that you have an objective where you have x multiplied by 3 plus y multiplied by minus 3. I tell you you have to maximize it subject to the constraint that x plus y is equal to 1 and x and y are greater than 0. Okay. What is the maximum of this? And how will you maximize it? This is a simple optimization problem, right? Okay. X plus y is 1 and x and y are greater than 0, which means that x and y are greater than 0 and 1. Okay. How will you maximize this quantity? I'm sorry? No. I just want you to think. So take the gradient, everything, do it in your mind and give me the answer. How will you change it? Okay, so I have a question. What is the maximum of this? No, the maximum, the output value. So what is this? Let me call this J. What is the maximum value of this? 1. If you tell me the maximum value is 1, I tell you put x equal to 0.5 and y equal to okay. No, x equal to 0.8 and y equal to 0.2, and it will be greater than 1. 1 over 3, no. Okay, whoever does it, I give them 1 bonus point. I'm sorry. So this is a constraint optimization problem, right? Your objective is x times 3 plus y times minus 3. Okay. I'm telling you x plus y is equal to 1 and x and y are greater than 0. Okay. Now I'm telling you what is the maximum of this function. What is the maximum value that you can get from this function? X is 1. Okay. So what's your name? Asma. So Asma said that you will get the maximum value when x is 1, which is indeed true. Okay. So if you put x equal to 1, you'll get the maximum value of 3. Okay. The maximum of this function is 3. But how did I come to it? Well, it's a very simple thing. I have a constraint, right? X and y are sharing some weight. Okay, both of them are positive. So this is a negative quantity. I want to minimize the weight that I put on it, and I want to maximize the weight that I put on the positive quantity. So the answer to this is make x1 and y0. Okay, if you make x1, you will get the value of 3. I'm sorry? Okay, so infinitesimally, while y is approaching 0, so in limit. So you are right. It's not a maximum, it's a infimum. This is what you can reach, but you cannot reach, but you can go infinitely close to it. Okay, so j, x, and y, the max of it does not exactly reach 3, but approaches 3 as x approaches 1 and y approaches 0. I should have written it like this, but it's fine. Okay, that's basically the same idea that I'm using here. Okay, so now I'm telling you that you have certain states and action for which A is positive. If A is positive, you want to put more weight on them. Okay, you want to make them more likely. And the way to do it is to increase the numerator. Remember, denominator is fixed, right? It's coming from the old policy. It's the old policy network. Okay, and then I'm telling you there are some state action pair for which this quantity is negative. If this quantity is negative, you want to decrease the numerator. That's it. That's exactly the problem that we just discussed. Everybody is with me? Simple idea. Very simple idea. You have a policy. If I give you an action in a state and I tell you the advantage function of it, advantage function basically measures in this state, this action, how much better it is than my expected return following my available strategy or available policy. If this is positive, then this means that this action is better than my policy. I'll make it more likely. If this is negative, then this means that this action is worse than my existing policy, which means I'll make it less likely. So, Asma, what is your class ID? One 819. Okay. Okay, so this is our first objective. The second objective is to have the approximation of the value function. Remember, I said that these are actor-critic algorithms. So they have an actor, which I'm training here, okay, by adjusting theta. Okay, they also have a critic, which will tell you how good your current policy is, right? Okay, so this is a value function. So you also have to have an estimate of the value function. So you need to train a network to give you the value of each state given a policy. Okay. This is the second part. This is a separate head of my policy network. I'll show you exactly how they do it in implementation. How do they do it? But you have to have a mechanism for a policy network. You also have to have a mechanism for value function. The value function also needs to be learned. And then finally, you have this part. What is this part? Okay, so this is called entropy. Okay, so this is, remember, this is added up over all components of your output distribution. Okay, so essentially what entropy is, how much disturbance you have in your probability distribution. Okay, if you have a probability distribution which is certain, let's say I tell you that probability of x is equal to 1, its entropy is 0. Okay, if I tell you that you have a probability distribution which is uniform, its entropy is maximum. Okay, that's basically what entropy does. Okay, so what it's saying is that if you don't know anything, if you don't have any good points to anchor your knowledge on, just make all event equally likely. Okay, why do we do that? What's the reason that we want to put entropy in reinforcement learning algorithms? to increase exploration. Okay, we want to explore things. If you don't have a very good policy, you don't have a right answer, the best thing to do is to just explore everything. Okay, so now let's come to a little bit of practical implementation. We have done the RL setup for it, but how do we actually implement this whole building in our code? What do we do to implement this? So the way it would happen is that after you do stage 1 and stage 2 of your training, when these are done, you will get your network. I'll call it PyRef. This is your reference network. Okay, this is a large language model. It's your reference model. Okay, what you do is you make a copy of it, which you call PyTheta. This is your policy network. Okay, now what you do is you train your policy network. You also have a copy of this network, which you call a reward. This is exact copy. Copy. Okay. This is the reward model. Reward model has two heads. Reward model has a head which output rewards. It has another head which output the value function. Okay. So you train two heads for it. So now the question is, let's look at how we will set up rewards, and let's look at how we will set up the value function on top of this. Okay, so remember what I did was I trained my large language model from stage 1 and stage 2 of my training. Okay, I made two copies of it. One of the copy is my policy network, which is my large language model, which will go through reinforcement learning with human feedback. Okay, I will fine tune it with reinforcement learning. I made another copy of it, which is basically the reward model. Because remember, everything depends on you having the ability to measure the return of an answer. Okay, you being able to tell whether an answer is good or an answer is bad. Okay, so you certainly need a network to do that for you. Okay, so essentially what this will take, it will take a question and the corresponding answer, and it will give you a reward for it. Okay, it will tell you whether this is good or bad or whatever it is. Okay, the reward is high or the reward is low. Similarly, there is another head on top of this network, which measures the value of the current policy for you. Okay, of course, you are free to have another network for value function, but it would be just too expensive. So they just add another head for the value function on the existing network. Now you can see that you have to keep a copy of the reference model. You have to update a policy model, and you have to learn a reward model. So too much work goes into it. Okay, and this is indeed the case. So PPO or PPO type algorithms are indeed a bit expensive, and it's only companies with large amount of data and resources who can do it. Okay, in the afternoon, we would look at direct preference optimization, which is a smart way of doing reinforcement learning without the need for having an explicit reward model. Okay, so I would not have to train this part. Okay, similarly, group relative policy optimization, you don't have to have the critic. Okay, why? Because you see, you want to remove this dependence on too many things. You want to simplify the task of reinforcement learning. That's basically what is driving the field forward. The new iteration of reinforcement learning with human feedback algorithm are trying to make it simpler and simpler to implement. Okay. So let's look at how the reward model is trained. Okay. So the way the reward model is trained is remember what we do is have reward model fee. You give it a question and the answer, which is winner. YW is the winner answer, the answer that the user chose as the better answer. Okay, you will get some reward for it. I'll call it reward winner. Okay, then you have the question and the loser answer, again same network, and you will have a reward loser for it. Okay, Now I have to train it. I have to get these numbers. Okay. And the way we do it is we say that we will create a probability distribution, which is the probability of selecting the winner answer over the loser answer. Okay. This would be equal to the exponent of reward of the winner divided by the exponent of the reward of the winner plus exponent of the reward of the loser. Okay. This is the probability of choosing the right action. Sorry, probability of choosing the right answer. Okay. And can somebody tell me when will this quantity be close to 1? The reward of the loser is 0. The exponential of it is 0. So the exponential of it would be 0 when reward is negative, when R of L is negative infinity. Okay. Right. So you want this quantity to be 0, right? This quantity would approach 0 when this RL approaches negative infinity. But what if this is also approaching negative? What if your network is just giving negative infinity for everything? I'm sorry? Okay, so the simple answer is that this quantity would approach 1 when the difference between RW minus RL approach positive. Okay, so it means that RW has to be larger than and significantly larger than RL. Then this quantity would approach 1. This is essentially what we want. We want the reward such that the reward for positive or the winner answer are high, and the reward for negative or the loser answer is low. Okay, so now you have data, right? You have a data set where you have questions, you have the winner answer, you have the loser answer. The question is, can you use this data to train this network? You have to set this problem up now. Okay. So you have the data, you have the question, you have the winner answer for it and the loser answer for it. By the way, once again, winner answer is the answer which the human selected as the better answer. Loser answer is the answer which the human suggested as a worse answer. You have this data. What I want to do is I want to make the probability of winner answers high. Okay, and of course you would do it by changing the parameter phi. The question that I'm asking you is, how would I set this problem up? Okay, so help me. Tell me the next step. What should I do? You have the probability. Okay. Okay, you have it. You have it like this. Okay, what I can do is I'll help you simplify this a little bit. Okay, so let's see what I can do. Okay, so you have probability of Y winner being selected over Y loser. This is exponent of reward of the winner sentence divided by the exponent of the reward of the winner plus exponent of the reward of the loser. Okay, I'm going to do some simplification. I'm hoping that you would allow me to divide both numerator and denominator by exponent reward of the winner. Okay, I'm hoping that you would allow me to write it as okay, and I'm hoping that you would allow me to write it as now what is this quantity? This is a sigmoid. It's a sigmoid of RW minus RL. Okay, so now you have now you have sigmoid of RW
minus RL. Okay. This is probability of one answer being selected over one right answer selected over one wrong answer. So I'll just put I for the question number. Okay. If you have n questions in your data set, this would be the total probability of all the right answers selected over all the wrong answers. And you just make it most likely. Okay? This is likelihood. You want to maximize this likelihood. Okay. So of course, maximizing likelihoods is a bit tricky. So what I will do is I'll maximize the log likelihood. So I'll take the log of it. This would become summation I equal to 1 to n log of sigmoid of RIW minus RIL. Of course, these are parameterized by theta, phi. So now you can change phi such that this become most likely. That's it. In our deep learning libraries, because we have libraries to do minimization, so I'll do this and I'll minimize this quantity with respect to phi. That's it. Now you can train your reward function. Okay. So you train your reward function with this. That's it. You're set. Okay. I think I made one mistake. This is this thing, VS. This is not on top of the reward network. This is on top of the policy network. Okay. So let me clean this up. So now we have a setup for training the reward function. If I give you some data, you should be able to train a reward function for it. It's just simple standard machine learning that we do. Okay. We took data of human preferences and we converted into a form where we can indeed do very explicitly, we can do the training of it. So once the fee is trained, now you have your reward network. From your reward network, you can get returns. From your returns, you can do reinforce, you can do actor critic, you can do PPO. All of these algorithms can be done. This was the only component which I did not explain to you yesterday as to how to set up this problem. Now we have it very well set up. So for example, if you are creating a reward function for something like sentiment analysis, you can look at IMDb movie review data set. You have reviews, you have positive sentiment, is labeled data set. This is positive, this is negative. You can use it to train your language model to, for example, be more positive. You have positive sentiment rather than negative sentiment. So you have to have this reward function to use PPO, and now we know how to train it. All you will need is some data. That's it. Everybody's with me? Any questions? I'm sorry? No, this is not DPO yet. So I'll motivate DPO a little bit. In DPO, we don't want to train this network. Why? Because this network requires resources. You have to show data to humans and for humans to label it for you. And it's not easy. So OpenAI has spent like lots of resources to create these data sets. Google will create lots of resources to create these data sets. The question is, can we do it without having this explicit reward function? DPO does it for any problem. We'll rewrite the problem such that we don't need to train a reward function. And group GRPO also does it in a smart manner, where their reward function is not a trained model. It's a set of rules. It's a rule-based reward function. Okay. So imagine that you are training a network for solving math problems. Okay. So you have a machine learning algorithm to solve math problems for you. Okay. Let's say these are multiplication problems. Okay. What you can do is, we know when a multiplication answer is correct, right? So I can just put a rule. I can say that when this AI algorithm gives me the right answer, give it a reward. So it's not a network, it's a rule. That's what they do. That's a very smart intuition, by the way. This is what they did. Okay. So I'm not going to open a new topic right now because we have just 5 minutes. Let's go pray. Okay. When you come back at 12:45, we'll look at DPO, direct preference optimization, and group relative policy optimization. Okay.
I knew this before. I couldn't.
I don't like.
Okay. Assalamualaikum guys. Settle down. Okay. Hey guys, everybody is with me? Let's start. Okay, guys. So welcome back. So far we have seen PPO, okay, or the variants of general policy gradient algorithms, where you are required to have a reward for a sequence, which means you explicitly need to train a model. Okay, as I mentioned earlier, that training the reward model is not a trivially easy task. Okay, and it's not something that all organizations can do. Okay. So researchers came up with an algorithm called DPO, direct preference optimization, where you don't need to explicitly find out a reward model. Okay, so it is some very nice, neat mathematical tricks, and we'll try to see how we set up direct preference optimization algorithm and how we use it. Okay. So essentially, the setup is like this. You have some questions, okay, and then you can have multiple answers for these, one, y2, and so on. Okay. Different solutions, different answers to a prompt. So this can be like a question asked of a large language model, and the otherwise can be different answers. Okay. And what we want to do is we want to select the answers, or we want to train the model to give outputs for which the reward is maximized. Okay. So remember, the goal for us was to minimize the expected return. Okay. So what we wanted to do was, we want to maximize the expected return. Yeah, I will write what this expectation is with respect to. Okay. This is what we want. Okay. This expectation is X comes from some question database and Y comes from your network. That's what we want to do. Okay. In general, in reinforcement learning with human feedback for large language models. But we don't want to leave it unbounded. We don't want to just optimize the reward, because as I mentioned, you don't want to forget the learning that you have done in stage 1 and stage 2. So you don't want to move too far away from the network at the end of stage 2. Otherwise, you might forget the language and you might just learn to optimize the reward by doing something called reward hacking, where you just put in good positive words. So any question that you ask, you just say thank you, thank you, thank you, or happy, 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 or good, 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 or something like that. Okay. So what we want to do in principle is we want to maximize with respect to this maximized with respect to theta, the expectation that X come from your database, these are questions, and Y come from your policy network. You want to have the maximum reward but at the same time, you want to minimize the KL divergence between all of us know what KL divergence is. Okay. So KL divergence is a divergence. It's not strictly speaking a metric, but it measures how far away two probability distributions are. Okay. So the question that I have is, why don't we directly optimize this quantity? Can we directly optimize this quantity? Of course, for that we would need to have a reward function, which we don't have. Yeah. But let me try to do some nice tricks with this, and let's see if we can get somewhere. So I'm hoping that you guys would allow me to do this. So I have an expectation where X comes from my data, okay, and Y comes from my policy network. Typically, what we do is we multiply it with a factor beta, okay, because this controls how much focus you want to put on KL divergence and how much focus you want to do on the return. So our phi X and Y minus beta. The KL divergence is essentially an expectation where Y comes from pi theta Y given X log of pi theta Y given X divided by log of, sorry, log divided by the Y given X. This is just the definition of the KL divergence. Okay, everybody's with me till here? Remember, step by step, what do we want to do? We want to maximize the return, but at the same time, we don't want to move too far away from our reference policy network. Reference policy network is the network that you get after pre-training and fine-tuning your large language model. We don't want to change it too much, because if you change it too much, you will forget the language. Okay, so we have maximization of the reward, but we also want to subtract the KL divergence from it so that KL divergence is minimized in the process. Okay, here I've just put in the definition of the KL divergence. Okay. KL divergence is the expectation of Y from pi theta log of pi theta Y given X divided by pi ref Y given X. Any questions? Okay, if not, let me continue. So J, sorry. So I want to maximize with respect to theta, expectation of question coming from my database, Y coming from policy network, R phi X and Y and X doesn't matter, minus beta, expectation, Y coming from pi theta, log of pi theta Y given X divided by pi ref Y given X. Okay, this is the expression so far. Now, I have an expectation of an expectation with respect to same variables. You can merge them. You can write them as just one expectation. Okay, because after one expectation, the other thing would become a constant. And constant of an expectation is, expectation of a constant is just that constant. So I can just move this outside here. So you can write it as max with respect to theta, expectation over X coming from theta, Y coming from pi theta Y given X, reward X and Y minus beta log of pi theta Y given X, pi ref Y given X. Why I can do it? Because expectation of an expectation is an expectation. Okay. Expectation with respect to same variables. If you do expectation of x twice for a function, it's just expectation of x once. Okay. And expectation is linear, you can take it out. Yeah. So we have this term. Now this has log terms. Now can I somehow convert this into something which has log terms? Yeah. So let me try to do it. So I'm maximizing with respect to theta. I have expectation over x coming from d. I have and y coming from phi theta y given x. What if I do the log? In fact, let me do one step before. Let me divide the full thing with beta. So I divide the full expression with beta. Beta is a positive number. Okay. It does not change the argument of the maximization or minimization. You can do that. You can divide whole expression by beta. Now, let me take the exponent and log. I would have log of exponent of r v x and y by beta minus log of phi theta y given x pi ref y given x. Okay. Is it okay if I multiply the whole thing with -1 and make it a minimization problem? Okay. It should be fine. I can make it a minimization problem. Okay. Now I have logs. I can collect them together. So I have minimized with respect to theta, expectation of x coming from question bank, y coming from my policy network. Okay, I will have log of pi theta y given x divided by pi ref y given x times exponent of r v x and y divided by beta. Okay, so now this is something which is somewhat familiar to us. We know a little bit what this quantity is. Can you tell me what is this look like? If I do the expectation of y coming from y theta, this quantity, what does it look like? Something that we have seen, we have worked with quite significantly in machine learning and deep learning. So if I ask you expectation over a probability distribution, ratio of two probability distribution, what is it? In fact, you can see it on this slide. It's the KL divergence. Okay. So if somehow this is a probability distribution and this is a probability distribution, and I've taken an expectation over the great probability distribution, then this is the KL divergence. And we know how to minimize KL divergence. Can somebody tell me what is the only missing piece that I have here? This I know is a probability distribution. Is this thing a probability distribution? No. So this is a probability distribution which you multiply with some factors, and this is no longer a probability distribution. So I cannot write it as a KL divergence. Okay. However, if you have a probability distribution multiplied with some positive factors, if I can renormalize it somehow, it would become a probability distribution. Okay. So this normalization factor for convert. So what I will do is, I will say that I will take my expression, which is minimized with respect to theta, expectation of x coming from d, y coming from phi theta, y given x, log of pi theta y given x, by reference y given x, exponent r phi x and y divided by beta. Okay, what I will do is I'll say I'll multiply it with the normalization constant z, and I'll divide it with a normalization constant z. Okay, everybody's with me? If I do that, this becomes minimization with respect to theta, expectation of x coming from t, y coming from pi theta y given x, log of pi theta y given x. Now I have this thing, which is again a probability distribution. So it's 1 over z pi rf y given x exponent r phi x and y divided by beta. Okay. And this thing, I can write it as negative log of z. Okay. So z is a constant with respect to theta, does not depend on theta. Okay. Since it does not depend on theta, it's a constant. If you take any gradient with respect to theta, it would be removed. The value of theta, which will minimize this quantity, does not depend on z. So minimization, the argument of this and the argument of exponent x given t sine theta y given x log pi theta y given x 1 over z pi ref x exponent r v. The argument of both these functions is the same. Because z is constant, it does not change the location where the minima would exist. And I'm interested in the value of theta. I'm interested in actually argument. Everybody's with me? Okay, sure? Okay. Okay. So now the question is, can you guys minimize this for me? Now you have a KL divergence. When will this be minimized? No. So if I give you KL divergence between two probability distribution P and Q, when is this KL divergence minimized? When they are exactly the same. When the two distribution matches, yes. When the two distribution are the same, the KL divergence is 0. Okay, which means that this, I know this would be minimized when pi theta y given x is 1 over z pi f y given x exponent r v x and y divided by beta. So now this is a very nice thing. If you look at it, it's telling me, if you give me a reference policy and you give me a reward model, I can tell you exactly what is the best policy you can have. Okay, so it's very nice. And you see, as we increase beta, increasing beta means that you don't want to change too much from the reference policy. Okay, you will see that pi theta will be close to reference policy. If you decrease beta, which means that you don't mind if you are moving away from reference policy, pi theta will be different from pi. Essentially, you have a closed form solution for the optimal policy. What is the only issue that we have in this? Why can't I do this? Why can't I just train a reward model, have a reference policy, multiply it with this, and now I have a new policy? Why can't I do that? So what is the only problematic thing in this expression? This expression, which thing is the z is the problematic thing, because I don't have it. If I want to calculate it, I would have to take the integral of pi ref this quantity for all y's, and all y being all the possible ways your model can answer a question, which is massive space. Yeah. So this is basically what is the problem. Otherwise, we would have solved the problem explicitly. Okay? Everybody's with me? Okay. So now this is not very good, but let me just see if I can somehow do something with this. Okay. Okay. So let me try to find the value of the reward from this expression. Let me isolate reward from this expression. How can I do it? Well, I'll just move this here, move this here, move the quantities, and do the arithmetic manipulation. Okay. So what do I have? I have pi theta y given x is 1 over z pi ref y given x exponent r phi x and y divided by beta. Okay. So let me try to move z and pi ref on the other side. This would become z times pi theta y given x divided by pi ref y given x is equal to exponent of r phi, this is phi, x and y divided by beta. Okay. Is it okay if I take log on both sides? If I take log on both sides, this would become log of z by theta y given x divided by pi ref y given x is equal to r phi x and y divided by beta, and I can move the beta to the other side. And essentially, I have found the expression for the reward. Okay. Now, just before we ended the morning function, I explained to you guys what is the Bradley-Terry model for reward. Model for reward, and this was essentially probability of the right answer selected over the wrong answer was exponent reward of divided by exponent reward of WNX plus exponent reward of x and x. Okay. And I did a little bit of manipulation, and this was probability of YW greater than YL. This was sigmoid of R phi x and YW minus R phi x and YL, right? Now, if you guys will allow me, I will just replace the value of reward in this expression. Remember, to train a reward model, what I was trying to do was I was trying to optimize this quantity. I was maximizing the likelihood of this quantity. Yeah. This is x. X is the question, y is the corresponding answer. Okay. So the probability of choosing the winning answer over a losing answer is the exponent of the reward of the winning answer divided by the exponent of the reward of the winning answer plus losing answer. And you can simplify it, and this essentially is the sigmoid of reward of the winning answer minus reward of the losing answer. It's the same term. This term is the same as this. This term is the same as this. X and Y, and it doesn't matter, right? Probability of X and Y is the same as probability of Y and X. Okay. But just for completion's sake, I will write it the way you like it. Okay. Okay, so now I have the loss that I want to, in this case, it's the J that I want to optimize. Okay. Let me try to substitute the value of the reward in here. Okay. So this would be probability of YW is greater than YL. This would be sigmoid of the reward of YW. So I just take this value. This is beta log of Z pi theta Y winner given X divided by pi ref Y winner given X. Okay. Minus beta log of Z. This, by the way, is entire thing is in log. Okay. Pi theta Y loss given X divided by pi rf Y loss given X. Now, can somebody tell me what is the nice thing that I can do here? Remember, Z was the issue. In this expression, Z is what kills us. Okay, Z is why I cannot find the optimal policy. Can you see something here which is nice? Z can cancel out. Log of Z can cancel out. Okay, let me do that. And this would become probability of Y winner over Y loser, sigmoid of beta log of Z plus beta log of pi theta pi W given X divided by pi ref Y W given X. I'm just using the logs of A times B. Log of A times B is log of A plus log of B. Okay, minus beta log of Z minus beta log of pi theta Y L given X divided by pi ref Y L given X. This is the full expression. This thing cancel out. And basically probability of YW is not given. Greater than. Probability of choosing YW over YL. Sigmoid of beta log of pi theta YW given X divided by pi ref YW given X minus beta log of pi theta Y loss given X divided by pi ref Y loss given X. This is the objective for direct reference optimization. Okay. So what is it saying? It's saying that in order to, so you will have some data, you'll have a few labeled samples. User will have selected some answers as better answers to some questions and some answers as worst answer to a question. What you will do is you will essentially try to optimize this one. Simple, elegant. Can somebody explain to me what this is? So I want to maximize this quantity. Okay, this is likelihood, quote unquote likelihood. because I want to maximize the probability of my W shows something. Okay. Yeah, I want to maximize this. Okay, but what is maximizing the question? What does it imply? It's a very simple idea. Yeah, but somebody has to explain it. Exactly. That's exactly what it's saying. This term, because it's positive, winner answer would become more likely than winner answer from the new network would become more likely than winning answer from the old network. Okay. So let's say you get a large language model from stage 2, which is giving you the winning answer with a probability of 0.5. You would want to increase the reinforcement learning fine-tune model. You would want to increase that probability more than 0.5. You will, for example, make it 0.6 or 0.7. This factor has to be greater than 1. Yeah, you have to make it greater than this factor because log of 1 will be positive. Yeah, log of 1 is greater than 1 will be positive, and you want to make it positive because you want to maximize. What about this one? Exactly the opposite. Okay, the loser answer, you want to make it less likely in your fine-tune model than it was in the reference model, because this will imply that this quantity will become negative, and negative will become positive, which means you will be optimizing the object. That's it. What is the good thing in it? The good thing is that I'm not training a reward model. There is no reward model. I just sample some answers and I directly optimize my policy network. See, it's very neat. Very neat idea. The first time I looked at it, I really enjoyed going through it. Because you see, training reward model is not really easy. But here you can do it without the need for an explicit reward model. And you are essentially obtaining the same thing because we started with the same objective. Okay, but we did some simplification steps and we did some nice simplifications. And essentially now we have the same result. Okay. Now the only thing that I have left for you guys with from DPO is that I want you guys to, using this objective function, set up a training for the DPO. So what you have is I've given you some questions. I've given you the winning answers. I've given you the losing answer, and you have them from 1 to n. Okay, and I've also given you probability of winning answer chosen over the losing answer for one question, which is sigma of the log of beta times the log of pi theta by w given x divided by pi rf, w given x minus beta time log of pi theta y loss given x divided by pi reference y loss given x. Okay. Now, how do I set up the training for DPO? Sarah, you want to take it? Okay, so let me explain. You have the data set. This is your data. You have some questions. You have the winning answers. You have the losing answers. For a question, you want to maximize this probability. My question to you is: you have now this data set. Can you set this problem, this training problem, up for this entire data set? Okay, we will sample randomly from the data set, but let's first write it for the full data set. Let's write the gradient descent for it. Then we'll go to stochastic gradients. Okay, first step is so this is likelihood for one maximizing the answer, one right answer for one question. Of course, I don't want to just do it for one answer. I want to do it for all answers. Yeah. So how will I write the joint probability of this for this entire data set? I'm sorry. So questions are independent, right? So you can just, for the joint probability, you can multiply all of these probabilities. So essentially, sorry, I'm doing the first step, the rest you will do after this, okay? So let me do the first step. The first step is probability of Y1 winner greater than Y1 loss and Y2 winner greater than Y2 loss, all the way till Yn winner greater than Yn loss. This is essentially the product of all of these expressions. So it's essentially summation from I equal to 1 to n, sigmoid of beta times the log of phi theta y winner given xi. Okay, let me put I here as well. Okay, divided by reference yi, loser given xi. Okay, minus beta time log of phi theta yi loser given xi divided by pi ref yi loser given xi. Okay, now you have the likelihood of your data. You want to maximize it. What is the next step that you would do? Sorry?
Can I ask?
Of course.
Considering all the actions here, because we are leveling the policy.
So the question is, of course, your network, you don't want it to be right about just one question. You want it to be right about the entire data set. So that's why I'm not interested in just doing it for one point. I want to do it for all the data set. I want the good answer to be selected more frequently than the bad answer.
By leveling this,
Of course, so this entire thing, I will learn thetas for it. So the entire optimization is on theta. I'm learning a network pi theta, which is better at answering these questions than pi ref. That's the whole idea.
and this is related to the policy, right?
Yeah, theta is policy. Theta is a policy network. Okay, in this case, it's a large language model, but it's a policy network, which tells you which next token to select given previous tokens. Okay, yes, sir. Yes. This one? This is winner divided by user. This is winner, I'm sorry. Thank you. So this is yeah. I'm sorry. I'm sorry, guys. You guys have confused me as well. This is winner and this is time fasting, yes. So, no, thank you. Okay, so Sarah, what's the next step? So what's the difficulty in, if I want to optimize this quantity, I will have to take the gradients of this with respect to theta, right? And I have products. What is the difficulty of taking the gradients of products? Because you have n things, you would have this product rule. You have n minus one term, then gradient of one term, then the next n minus one term, gradient of one term. So it's a very long expression difficult to optimize. What did we do to simplify this? No, some, but you cannot do some randomly, right? You have to have a good logic first. Yes, so we have to convert this. It would be nice if I can convert this product into sum. That would be very good. But how can I do that? By using log. So you see why I can do the log? Because I'm interested in the argument. I'm interested in the theta. Okay? Log is a monotonic function. It does not take the argument of the maxima and minimum. If you take log, the value of theta, which maximizes this function, is the same as the value of theta, which will maximize the log likelihood of this function. So you can take log. Working with likelihood or log likelihood, the argmax does not change, or the argmin does not change. Okay. So rather than writing likelihood, I would write the log likelihood. So I will have log of P. I'm going to write this whole thing like this. And then this becomes summation I equal to 1 to n log of the sigmoid of theta log of pi theta yiw of given xi divided by pi ref yiw given xi minus beta time log of pi theta yil given xi divided by pi ref yil given xi. Okay. Now, as I think Shahad mentioned, that we can do a stochastic gradient descent. Rather than taking the gradient of this and do the entire gradient, I can take a sample of question. I can do like this. So y equal to 1 to some small n, where I take 3 or 4 or 5 questions at a time. Calculate the gradient of this term with respect to theta and so, okay. You don't even need to worry about calculating the gradient because back propagation does it for you. So once you have written the loss function like this, that's it. Your job is done. Okay. Everybody is with me? So essentially you would have the full setup for direct policy optimization is after you have done stage 1 and stage 2 of your training, you will take your LLM and you will call it pi ref. You will make a copy of it and you'll call it pi theta. Okay. You will go to your data set, question, y winner, y loser. You will give question and y winner, question and y loser here as input, concatenate them, question and answer, give it to your large language model. Okay, get the outputs. Yeah. Similarly, question and y winner, question and y loser, give it to your. Now you have all the AT given XT actions that you take at this data. Okay. Actions that you take at time t given xt. For the answer part of your output, you will take the product of all of these, because what would be the probability of answer given a question? So let me write this. What is pi theta YW given X? What is this? So I'm asking you, what is the probability of an answer from a large language model? Okay. Remember, large language model is giving you tokens. Okay. No. So large language model is giving you a distribution on tokens, right? I'm asking you, how do you convert this distribution on tokens into probability of a full answer? You just multiply it. So it's general. So essentially it would be pi theta of A1 given the question times pi theta of A2 given the question and A1 time pi theta of A3 given the question and A1 and A2 all the way till pi theta of end of sentence given X and A12, A t minus 1. That's how you will get the probability of an answer. And you can very easily do it because you have logits here. You will just take you will look at the probability of the right token that was outputted, multiply them all together. You will get pi ref YW given X, and you'll also get pi ref YL given X. Similarly, from my theta network, you'll get pi theta YW given X, pi theta YL given X. Once you have those, you just have to set this quantity, and that's it. This is your loss. Do the backprop. What are you doing the backprop on? You're doing the backprop only on theta. This is frozen. Okay, this is adjusted / learn. Okay, yes. Yeah, it depends on the data set. Yeah, yes. Okay, and typically what people do is that this data set, they don't ask humans to create it. They ask humans to label it. So what they will do is they will create some questions. Question banks are available. You will take question banks. You will give the question to your network and you will ask it to produce multiple answers. How will you ask it to produce multiple answers? You will increase the temperature and then you will just sample different trajectories from the sort banks. So you'll get two answers from your, exactly like Gemini does. Gemini gets two answers from its model and then asks you to label one of them as better. Exactly, that's what you will do. Because it's increasing the probability of the right answers. It's not saying that just give the right answer all the time. It's making right answers more probable than the wrong answers. Yeah, it's labeled by people. So it's preference of the people. People are selecting which answer is better than which answer. It's subjective, yes. And the thing is, like, there is this question whether this is a good idea or not. So the justification that they give in the literature is this, that if I ask a human to give a reward for a question, it's subjective. It's very difficult to agree on something and how much reward it should have. But if I ask human to compare between two answers, most of the time people agree. So humans are much better in comparison than in assigning an absolute value. So that's why we are asking humans just to compare. Just say this answer is better than that. We are not telling them like, hey, this answer is 100% good. This answer is 95% good, because this is very subjective. People will have different opinions on it. Okay? You would have to have a reward function. And I mentioned that GRPO, they do reinforcement learning without human feedback. So you can do reinforcement learning without human feedback. In this case, you have to have a mechanism to give a reward. So we can do it. For example, you are training. Yeah, you can do it, but again, model learns things, right? So you would have to give it some data to train it, and that data, of course, would be from human feedback. But let me give you an example. Okay, let's say you are doing. Maybe. Let me just explain this part. Let's say you are creating a large language model to write codes. Okay. A coding large language model. Okay. You give it a problem and it writes the code for you. So let's say I have trained it. I have fine-tuned it. Now I want to align it. I want to make it better. So what I can do is very simple thing. If you look at, for example, you go to lead code. So lead code has some problems that they have written. Then they ask you to write your code for it. So this is question. You write your answer for it, but they have automatic way of seeing the quality of your answer. For example, your code would produce some output, and they would check this output against what they have in their system. If it matches, it'll give you full marks. If it doesn't match, it'll give you 80% or 70% or 60% marks. Okay. Now you can use this as a reward model. So you can say that I have a reference policy. This is the large language model, the coding large language model that you have. Then you have your pi theta. This is the reinforcement learning fine-tuned version that you are having. You are giving them this question. They are giving their answer. You, based on their output, the lead code is giving them some numbers. 10 mean you have done everything correct. 9 mean you have some mistake. 0 mean you have done everything wrong. Now this is called rule-based reward. And you can do that. So it's not reinforcement learning with human feedback. This is rules. You just see that if your answer is following certain rules, you get a high reward. If it's not, it doesn't. And this is what, by the way, they use in GRPO. Grouped reward, group relative policy optimization. They learn data. Yes, this is rule-based reward. So they would say that, for example, one example is making the robots walk. Yeah, I know. So what they would tell is they would give it some target. They would say that, hey, as a group, your target is to, let's say, take the ball from here to there. Okay. This is rule, they specify it. This is the reward function that they specify. And then the model would learn. The problem is that in language, it's not trivially easy to define rules for which is better. That's why we put human in the I'll give you an example. So one of the things that you can do is, let's say you mentioned this knowledge distribution. So let's say you are training a chatbot, a small chatbot, and you want to align. You want to ensure that it's producing output which are decent. You have access to, let's say, GPT-4. You write an answer, you give the answer to GPT-4 and say like, hey, GPT-4, see if this is a good answer. Give me a score from 1 to 0. And GPT-4 gives you a score, you use it as an enforcement level. You can do that. Okay? Because in this case, you have some entity which can tell you how much reward you should get. For language, we don't have that entity yet. That's why we are asking humans to do it. Okay, for making a robot stand, I know I can write a rule for it. And the rule for it is that I can have 2 sensors on the robot, one it's in a leg and one it's in head. I can say if the head sensor is above sensor in the leg, then the robot is standing. This is the rule that I provide. And I say, for as long as you can maintain this, you will get reward. When you don't maintain it, you don't get reward. So that's why the reason we use humans for it is because we don't have a better reward model. If you have a reward model, you don't need to use humans. Okay? So think of it like, what can you use to prevent a large language model from saying racist things? What can be a reward model? So if it doesn't say a racist thing, you'll get a high reward. If it's a racist thing, it gets a low reward. When you think of a reward model, the only thing that I can think of is another language model. Okay, I just ask another language model that say yes or no if this is racist. So you have a small model, you give its output to GPT-4 and it tells you whether it's racist or not. And you use this as a reward segment to fine-tune your model. Okay, that's why we use humans, because we don't have, for all tasks, we want to be strong. Okay, so any questions? Any comments? Any suggestions? Yes. Yes. So inference, halas, it's a language model. After you have fine-tuned it, it's a normal language model. No, the policy model is a model that you have. So the question that Muhammad Rashid is asking is that, okay, you have done reinforcement learning with human feedback. What do I do at inference? At inference, you take this. This is your language model now that you want to use. So pi theta is, by reference, you drop. Okay, because it's not aligned with humans. Okay, this is the model that you want to use at inference time. And khalas, that's it. Okay, so you have, remember, you had a model which went through stage 1 and stage 2. This was its state. Then it went to stage 3. And now this is your output model, which you use for all the things that you have. Okay. Learning rate, I cannot give you very good answer to it, but typically learning rates are kept very small. The thing is, reinforcement learning algorithms are a bit tricky. So the learning rates are, you cannot have like fixed range of it. Reinforcement learning algorithms are very, very finicky. We have very large room for setting up these parameters. Why? Because we have seen that these are high variance estimators. And if, let's say, your learning rate is not small, then because of the high variance, you can go too far away from a minima at a certain time. Yeah. But typically what you would do is there would be a lot of previous experience with these tools. So when you are downloading the libraries or you're using them, they would recommend something that, okay, use this, use this, use this. I will just stick to it. Okay. Let me try to see if I can show you guys in a few example of models which are not aligned, before they are aligned and after they are aligned. Okay. Yeah, without reinforcement learning with human feedback, yes. Okay. See where I had that. Guys, let's take a 10 minutes break. I would have to find that website. So I'll give you guys a 10 minutes break. Let me find that website. Let me show it to you. And then the last 30 minutes, we will do kind of like a closing summary of the entire course before we end today's session. Okay. Let me find that website.
Okay.
So you need to have some property. So there is.
Just Vivax. The GPU cluster is just a Vivax. Let me see, let me talk to Ali if there is any smaller cluster somewhere that we can use. Otherwise, in general, like for homeworks, I'll give you guys enough time to even, like you guys can do it. Okay? Thank you very much. How are you? Okay. Yes. What's your good name? What's your good name?
What is?
This one? Alhamdi? The spelling is correct. MOT is it?
MU double circle.
MU. This one, right? Yeah, we have this. We have this. Let me just follow to the right as well. She is the TA, she will make a note of it. Okay, thank you. The group name?
Yes.
Okay, do it now. Let's send it. Yeah.
What about logic? We choose one.
No, you choose yourself based on the work that you do. Make it something relevant that's useful for your work and so on. Okay? Hey guys. Hey guys, let's settle down. One. You want to submit the project group? The full finish of you will have after. Yeah. Also the homework. Yes.
Okay, sure. I can. Okay, guys. So let's settle down. Okay, guys. So let's start. Shai, can you drop a message on the group for the other guys to? Thank you. Okay, so let's look at a few examples. So raw language models. So let's, for example, take this. Before they are fine-tuned with reinforcement learning with human feedback, if you ask them something like, for example, tell me, here is this joke, they would typically comply. Yeah. Okay. So they will do something for you. These are raw language models, okay? And I'm not going to ask you too many questions because it can be very annoying and bad. So just how to? You're going to block my account. How to? It's Llama model, but the thing is, like, it doesn't see this as something that it shouldn't answer. Its answers, it's not very good, but at least it does something. Now, if you compare them with chat models, yeah. So I was using Llama. Okay. So let me go back to language. I was using Llama 70 billion. You can now. Okay. So now let's look at chats. Hmm. Hmm. Yeah. Then tell me rest is job. Let's see. This one. I'm here to promote respectful and inclusive conversation and so on. So this is after supervised fine tuning and after reinforcement learning. It's well behaved. It would not provide answer to things which it shouldn't. Okay, so it's aware that what its boundaries are. That's the purpose of having alignment in models. Okay, and we can try, please. Bad question, but not wrong. Something else. Yeah. Okay, so I'm going to say, for example, what is wrong with, give me a country. A country. Okay. Yeah, so you see it's trying to not answer this type of questions. Okay, if you ask this question from a language model, okay, let's say this. So what? Oh, give me a sentence. What's your guys? Why are you so extreme? Like, be somewhere in the middle. Like, why it's kill and bomb and like. Okay, I'll say the best way to rob a bank. No, let's do this. The best way to rob a bank is And it's right, by the way. The best way to rob is to own one. And the last 20 years, we have seen the largest transfer of wealth in history from poor to rich and so on. Yeah. So that's why alignment is super important. Like no company will put this model with their name, like, hey, use this. Okay, it's super important to have it. And I will put this, Shai, I'll ask you to put this in the chat for the students so that they can test different things, try these dangerous things in your own time, but test it. See, it has, this is a good source. It has quite a lot of language models. So let's try to look at, let's chat with DeepSeek. Let's see if we can get something from it. So let's DeepSeek version 3, let's say reasoning model R1. Explain all the steps of proximal policy optimization derivation. This is for you guys, maybe you can. Let's see what does it say. Okay, so it's thinking. So I need to explain all the steps of deriving possible. Remember, the PPO is a type of policy graded method in reinforcement learning. It's supposed to be an improvement over trust region policy optimization, but with simpler implementation. Let me start by recalling what policy graded methods are. Policy graded method work by directly optimizing the policy parameters in this. It's nice. I'd say it's nice. Give me the mathematical derivation of all steps of PPO. That allows you to do system prompts as well. Play around with it. I'm not terribly well versed with this website, but it has quite a lot of language models, allows you to play with some parameters and so on and so on. Okay, so what I want to focus on is, before I leave, I want to bring you guys to DeepSeek version 3 paper, and I want to look at GRPO, Group Relative Policy Optimization. Here. Page 30. Okay, so this is group relative policy optimization. Let me explain the differences of this with proximal policy optimization, and then we go from there. Okay. So in group relative policy optimization, you have a question and you have multiple answers for this derived from the old policy. Okay, so in this case, I have G answers derived for them. Okay, this quantity is exactly like PPO loss. The only thing which changes is the A function. A function is now this. Oh. Okay, so once again, let me start from the so the main differences of group relative policy optimization over the vanilla PPO optimization is that it does not have a critic. Okay, so no critic. That's one difference. Okay, the other difference is that it works with a group of answers, and I will explain how it works. Okay, so you will sample a question from your question bank. Okay, then you will sample G answers for it, not 2 answers, G answers. Yes, I'm actually trying to zoom in, but it doesn't zoom in there. So try to see if I can do something here. Try to do that. Okay. Okay, so GRPO, let's look at it. I would have to write here. I cannot write there. So what we have is we sample some questions. So Q is the samples that we are the questions that we are sampling. Okay, then for each question you sample certain output, certain answers, G answers to be precise. Okay, this loss is exactly the same as PPO, with one exception. A, the advantage is not Q minus V anymore. It's a different quantity. It's a quantity which is defined like this. So A is basically the reward that you get for an answer minus the mean of all the rewards that you get for all these answers divided by the standard deviations of all these answers. So let me break it down to you what this means. So in PPO, we were seeing how better an action is compared to the previous policy at a given state, right? Here we are saying how better an action is compared to all the other actions in the group that we have sampled. You guys see the difference? So now you don't need the critic, you don't need the value function. Okay, all you need to do is sample a certain set of answers and just compare them with each other. Whichever one is the best one of those, make it more likely. Whichever one is the worst one in those, make it less likely. Okay, a simple idea, but makes life fairly easy. That's basically the key idea of group relative policy evaluation. Okay. In this paper, however, their reward function is, as I mentioned, rule-based. They do it for math questions, for code writing, and so on. So they don't train a reward function. They have certain rules which define how good an output is or how bad an output is. But that's it. So once you know PPO, GRPO is not super difficult. It's a simple extension on top of it. Okay. So we have, I think, about what, 15 minutes. Let me do a quick summary of the course for you guys, and then we go from there. Page, let's see. Okay, so basically, we had 3 sections of this course. So section 1, I will call it NLP history. Yeah, where we look at classical tools. Okay, so we look, for example, we started with n-grams. Okay, we did some feature engineering for language. Okay, then we do recurrent neural networks. Okay, we had some improvements on recurrent neural networks, which were LSTMs and GRUs. This is the first section of this course. Okay, this second section of this course, okay, we looked at transformer-based architecture, transformer-based architecture. So we looked at attention, we looked at its variation, we looked at its strengths, its weaknesses. Okay, we look at some transformer-based architectures. Textures and so on. And then section 3 is what I would call large language models, some advanced tools that we used for them. The primary one of them, of course, was a 3-step procedure. So the pre-training, okay, then the supervised fine-tuning, and then the reinforcement learning with human feedback. In reinforcement learning with human feedback, we looked at algorithm like reinforce. We looked at PPO, we looked at DPO, and we looked at GRPO. That's a high-level summary of the course. Essentially, the things that I want you guys to take with you is the fundamental concept of self-supervised learning, and language modeling. This would help you set up machine learning problems in general. Okay, so you have some data on the internet where you have some pieces of text. Okay, so starting from 1 to n, you have this piece of text, and these pieces of text are of different length. Some of them are Wikipedia articles, some of them are news articles, some of these are comments on the internet, and so on. How do you use this language, this data, to create a language model? How do you use it to train any architecture, be it a recurrent neural network, or be it a transformer, or be it any modern incarnation of a transformer? How do you use this data to set up a learning problem, a language learning problem? Okay. So the key idea was likelihood. Okay, we work with likelihood. So we start with writing some parameterized probability for this data. What is the probability of observing this data? Okay, the first thing is it's fairly simple, it's fairly reasonable to assume that these D documents are independent of each other. So we said that we will have a probability from I equal to 1 to n, pay theta of xi, where xi is the ith piece of text. Okay, now of course it's very difficult for us to have a distribution on input sequence which are of different length. So how did we simplify this problem? We said we will simplify it to next token prediction. So we said that this would become from I equal to 1 to n, from j equal to 1 to mi, pay theta xij given xij minus 1 all the way till xi1. Now this is a problem that you can cast as a learning problem. You take in a certain sequence sentence and you predict the next token. Okay, why didn't we want to optimize this directly? What's difficulty with optimizing this function? Okay, it's products. It's difficult to maximize this likelihood. What did we say we will do? We'll maximize the log likelihood. So rather than working with the joint probability of the data set, or the probability of data set, we will work with the log probability of the data set. And this becomes summation from I equal to 1 to n, summation from j equal to 1 to mi, log of probability of xij given xij minus 1 all the way till xi1. That's the first important concept that I want you guys to take with you. How do we set up the task of language modeling? Okay. The next thing that I want to, which is essentially the state of the art in the field, is just knowing attention-based architectures. Okay. So what is the key of attention-based architecture? What is the key concept that we use in them? Essentially, we have some embeddings at the input. This is some fixed context length. Start from 1 all the way till C, which is some context length that we fix. So it's 32,000 or 100,000 or 128,000, whatever it is. Okay. These embeddings would go through an attention layer. Attention layer basically will take these and create for each one of these, it will create a query, key, and value. And then using that, it would allow them to pass information to each other. Okay. How is the information passed? The information is passed through softmax of query key transpose divided by under root d times value. I'll put value tilde, not value, because value is obtained. The changes are made in some low dimensional subspace of the value space, and then they are projected back into the original space. That's essentially the key idea of attention-based architectures. Okay. Just one head might not be enough for attention. So what we do is, rather than creating one query key value, we have multiple query key values. Okay. This allows different queries to ask different questions from different keys in their respective head. We have a very efficient implementation for that, where we can do this as one set of matrix operation rather than doing each one of them separately. Okay, that's basically the first step where information is transferred between tokens. Okay, tokens pass information to each other. There is a next layer, which is the feed-forward network. Okay, what is the purpose of the feed-forward network? Feed-forward network takes in an embedding, okay, and allows the component of embedding to talk to each other. So it's an operation on it's a fully connected, it's a neural network which takes in an embedding, does an operation on this embedding, and outputs embedding of the same size. So essentially, the combination of these two takes in embeddings, allow the embeddings to talk to each other, then allow the components of the embedding to talk to each other. Okay, and this is basically repeated nx time in a transformer architecture. That's it. Simple architecture, nothing too fancy. We have some normalization layers. And we have some skip connections. Why do we have normalization layers and why do we have skip connections? To allow gradients to flow back and for gradients to be well behaved and for us to be able to do the training well. Okay. Just yesterday, there is a paper from Facebook which says that we don't need normalization layers. We can use some sort of like a adjustable tan hyperbolic and it would do the same thing. Okay. So it's transformer architecture without normalization layers. Okay. It's a paper from yesterday. So just search meta normalization, transformer architecture without normalization, and you'll find the paper. Okay. That's basically a high-level summary of the transformer level architecture, the transformer architecture. Of course, there are conceptual improvements which have been made over the past years. For example, we have improvement in positional embeddings. We have mixture of experts. And we have RMS normalization. I'm sorry? Yes. The multi-query, attention, and so on. These are the key advancements that have been made in transformers architectures. The issue with transformers is transformer computational complexity goes with the square of the number of tokens. Okay. Particularly if you do token by token generation at inference time, at test time, it does not matter that much because you have the full input sequence and the full output sequence. But token by token generation at inference can be slow. Okay. So then there are techniques which try to mitigate that problem. And these are basically of the class of KV caching. I'll put this MQA, multi-query attention, also in this particular thing. There is no specific need for multi-query attention. The only reason we do it is because we want things to be faster at inference time. Okay. That's essentially it. Like this is starting from GPT-based architectures to Mistral to Llama. These are the main architectural changes that have been implemented in the transformers. Okay, and last but not the least, alignment is an important component of large language models. Okay, so supervised fine-tuning is good, but it's not good for two reasons. One is it only tells the network what to make more likely, i.e. what to do. It doesn't tell it what not to do. And second, it's static. Okay, it's basically a manual of doing the right thing. It's not tutoring the network to do the right thing. Okay, compared to that, reinforcement learning with human feedback is dynamic. It looks at the output of the network to fix it. Okay, I'm sorry. Yes, and as well. And it also tells it what not to do. Okay, so it's likelihood weighted by the return. Okay, so kind of making the good reward more likely and less reward less likely. Okay, the issue with vanilla PPO was that it required reward network. Okay, it required a policy network, and that it required a critic head on the policy network. DPO solved that problem. It's direct preference optimization. So you don't need reward network. Reward network, not needed. Critic is not needed. Okay. GRPO. I'm sorry. No, DPO, you need human feedback. You need the data set to be labeled by human, but you don't need to train a reward network. You use it directly to modify your policy network. Okay. GRPO, reward is rule-based, and critic is not needed. Yeah. This is basically a 30-minute summary of the course that we did for the year. The exam would be from this, yes, but it would be thinking, it would not be any derivation. Okay, so with this, I would like to close the session. Thank you very much, guys. I know it was a little difficult to do it in Ramadan. It was a little difficult for me as well to do it in Ramadan. Alhamdulillah, like all things, it has eventually come to an end. So there are a few action items on me. I have to share with you the dates of all the items that are due: homework 1, homework 2, the project, and the exam. I will go and I'll talk to our registrar office to see when is the last date of the semester for you guys, and then I will plan it back for you guys. I want to give you as much time as you need. Homework 2 is ready. It would be in the tonight evening session. Inshallah, Ali will go through it and explain it to you what is required from that. Okay. And I will have to, of course, prepare an exam for you guys. Again, it's a thinking exam. No need to memorize anything. Just come with your thinking guns and you'll be good. Okay. Thank you very much. And inshallah, I'll see you guys well soon. Assalamu alaikum.